Hello, in today's class we will talk about voltage and current division. Before we discuss voltage and current division, let us first review what you learned in college about combining resistances in series and in parallel. First, we talk about series combination. We have two resistances R1 and R2 connected in series between node 1 and node 2. We want to replace them by a single equivalent resistance Req between the same two nodes. Then Req is equal to the sum of the two series resistors. In case of parallel combination, we start with two resistances R1 and R2 connected in parallel between node 1 and node 2, and we want to replace them by a single resistance Req. In this case, the combination formula works in the reciprocal domain. That means the reciprocal of the equivalent resistance is equal to the sum of the reciprocal of the individual resistances. This formula and this formula both work even when more than two resistors are in series or when more than two resistances are in parallel. For a specific case of two resistances in parallel, we can express Req directly using this equation. Now we go to voltage division first. The voltage division is described by what is known as the voltage divider rule or VDR. We have two resistances again R1 and R2 connected in series, and the series combination is connected to a voltage source Vs. That means Vs is the voltage, total voltage across the series combination. Vs is known, R1, R2 are known. What we want to find out are the voltages across each resistance. That means what is the voltage V1 across R1, what is the voltage V2 across R2. We should also look at the relative polarities of the voltages. If we go clockwise, Vs is a rise while V1 and V2 are voltage drops. This one is a series circuit, so the current is the same through every circuit element. Let's say the current is I and flowing in the clockwise direction. This I and V1 satisfy passive sign convention. This I and V2 also satisfy passive sign convention. So we can express V1 and V2 using Ohm's law according to this relationship. V1 is plus IR1, V2 is plus IR2. So if I know I can find out V1 and V2. To find I, we combine these two resistances in series. So Req is R1 plus R2. The current will remain the same because series combination of resistances does not change the current. So if this current is I, using Ohm's law, the voltage Vs is now across Req. Using Ohm's law, we can say I is the voltage divided by the sum of the two resistances. Okay, so if I plug in this value of the current in these two equations, we can write V1 is Vs R1 by R1 plus R2, and this is V2. These two rules are known as the voltage divider rule. These rules allow us to calculate the voltage across each resistance when I know the total voltage and the value of each resistance. In order to remember the rule easily, it helps if we look at the structure of the equation. In both relations, there is a common part. The common part is shown in bold, Vs divided by R1 plus R2. So, in voltage divider rule, every voltage has a common part, which is the total voltage divided by the sum of the two resistances. To find the voltage across a resistance, we have to multiply by that resistance, by the same resistance. That means if I want the voltage across R1, I will multiply the common part by R1. if I want to know the voltage across R2, I will multiply the common part by R2. Okay, so these rules are very useful in analyzing electrical circuits. Next we move on to current division, which is expressed by the current divider rule or CDR. Let's say we have two resistances in parallel, R1 and R2. The total current going into the parallel combination is IS. This IS current divides into R1 and R2 as I1 and I2. I1 is the current flowing through R1, I2 is the current flowing through R2. Our intention is to find out I1 and I2 from our knowledge of IS, R1 and R2. The resistances are connected in parallel. We know that for parallel connection, the voltage is the same. Let's assign the voltage V across these two parallel combination. Okay, so V is the voltage across R1, V is also the voltage across R2. And we can observe that this V and I1 satisfy passive sign convention. Similarly, V and I2 also satisfy passive sign convention. So using Ohm's law, I can write I1 is the voltage divided by the resistance, V by R1, and I2 is the voltage divided by the resistance, V by R2. So if we find out the expression for V, we can easily determine I1 and I2. Okay, we combine these parallel resistances into an equivalent resistance, and in parallel combination the voltage does not change, so V remains the same. For combining two resistance in parallel, we use this specific equation, and using Ohm's law I can say V is Is time Req, because this Is and this voltage V in resistance satisfy passive sign convention. Okay, so V is Is Req, that gives us this equation. So if I divide the voltage by R1, I will get I1. If I divide this voltage by R2, I will get I2. The equation of I1 is this, and the equation of I2 is this. These two relationships are known as the current divider rule. Again, if we look at the structure of the equation, we see some pattern. There are common part in both equations shown in bold. Is divided by R1 plus R2 is the common part. So what is the common part? The total current of the parallel combination divided by sum of the two resistances. This is similar to the common part of voltage divider rule, which was total voltage of the series combination divided by the sum of the resistances. But to find the current, what we multiply the common part with, that is different. In case of voltage divider rule, we saw that to find the voltage of R1, we multiply common part by R1. But here, to find the current of R1, we multiply the common part by R2. In voltage divider rule, we multiply common part by the same resistance. In current divider rule, we multiply the common part by the other resistance. So you need to remember the similarity and the dissimilarity between voltage divider rule and current divider rule. We can represent the comparison between VDR and CDR for two resistances. This comparison table will not hold if we have more than two resistances in series or more than two resistances in parallel. So for two resistances, this table tells us what are the comparisons. First, when applicable, voltage divider rule is applicable for two series resistors. Current divider rule is applicable for parallel resistors. Never try to apply VDR for parallel resistors. The voltage remains the same in parallel connection, and never try to apply CDR to series resistors, because in series connection the current is the same. Now what do we calculate with these rules? With voltage divider rule, we calculate voltage across each resistor. With current divider rule, we calculate current through each resistor. Okay? And what is the common part on the right hand side of the equations? In voltage divider rule, the common part is the total voltage divided by the sum of the resistors. In current divider rule, the common part is the total current divided by the sum of the resistors. So the common part in both rules are similar. And to find a voltage, what do we multiply the common part by? The same resistance. To find the current through a resistor, what do we multiply the common part by? By the other resistance. So this is the important difference which you should remember. Okay. Now we will look at two special cases of voltage divider rule and current divider rule. First, we considered the situation when we have a resistance in series with an open circuit. R2 is an open circuit. We have already discussed that an open circuit means infinite resistance. So let's apply voltage divider rule to this situation to calculate V1. V1 is, we know, Vs R1 divided by R1 plus R2. But now R2 is infinity. Vs is finite, R1 is finite. In the denominator, R2 is infinity. So the result is 0. Okay. So if V1 is 0, then Vs is equal to V2. That means the entire voltage Vs drops across the open circuit. And if the voltage across R1 is 0, according to Ohm's law, the current through R1 is also 0. When the voltage and current of a resistance is 0, the resistance is not doing anything in the circuit. The resistance is electrically inactive. So we can generalize this finding. By generalizing, we can state that a resistance in series with an open circuit is electrically inactive. Okay? The next case is resistance in parallel with a short circuit. We consider this situation. R2 is a short circuit, and we know that a short circuit means the resistance is 0. Now we apply CDR to calculate I1. I1 is Is R2 divided by R1 plus R2. Now R2 is 0. So in the numerator we have 0. But R1 is not 0, so denominator is not 0. As a result, the I1 current is 0. If I1 current is 0, Is equal to I2. In other words, all the current is flowing through the short circuit. No current flows through the resistance. If the current through the resistance is 0, according to Ohm's law, the voltage across the resistance is also 0. If the voltage and current of a resistance in a circuit is 0, the resistance is not doing anything in the circuit. It is electrically inactive. So we can generalize our observation in this way. A resistance in parallel with short circuit is electrically inactive. So we have learned about two situations when a resistance in a circuit can be electrically inactive. First, if the resistance is in series with a open circuit. Second, if the resistance is in parallel with a short circuit. These are very useful rules to simplify circuit analysis in practical cases. We will remember this for the rest of the course, actually for the rest of your professional life. Now let's solve a problem. Always the proof is in the pie, and whether we have understood the concept is in our ability to solve circuit problems. The circuit is given we have been asked to calculate the current I1 through this 6 ohms resistance using either voltage divider rule or current divider rule. We are allowed to use any of the two rules, but we are not allowed to use any other technique which will not involve VDR or CDR. I will show the solution using CDR or current divider rule. Okay. First step in solving almost all circuit problems is to identify the nodes in the circuit. This is a simple circuit. We see that there are three nodes, 1, 2, 3. 3 ohms resistance and 6 ohms resistance are connected between the same pair of nodes, so they are in parallel. If they are in parallel, we can combine them using the parallel combination rule, and the equivalent resistance of these two is 2 ohms. So we can simplify the circuit. The 8 ohms remains, the 20 volt remains, and the parallel combination of the two resistances is replaced by the equivalent resistance 2 ohms. Now, I have a question which is a very important question. The current through this 2 ohms, is this I1? I1 is which current? I1 is the current that is flowing through 6 ohms. When I have combined 3 ohms and 6 ohms in parallel, this 6 ohms resistance has vanished. It has disappeared. When the resistance vanished, the associated current also vanished. So in this circuit, there is no I1 current. The current through equivalent 2 ohms is not I1. This is a different current. This is an important point which you have to understand. So this current is not I1. Let's give it a different name. We call this current I0. Okay. Now the next question is, what is the current which is flowing through 8 ohms from left to right according to this arrow? Is this I1? Of course not. This is not the 6 ohms. But if we look at the circuit, this 8 ohms resistance and the 2 ohms resistance, these two are connected in series. Only two circuit elements at this node. So 8 ohms and 2 ohms are connected in series. We know that series connected elements carry the same current. So the current through 8 ohms and the current through 2 ohms in the same direction are the same. So which current is this? Yes, this current is I0. The current through 8 ohms is I0. The current through 2 ohms is also I0. And remember again, I0 is different from I1. Okay, now 8 ohms, 2 ohms are in series. We can combine them. The equivalent is 10 ohms. And I have already mentioned before that in case of series combination, the current does not change. So the current through equivalent 10 ohms is also I0. In this circuit, we can easily calculate I0 using Ohm's law. I0 is 2 ampere. Now, I0 is the current flowing through 8 ohms from left to right. And in our original circuit, we have this 8 ohms resistance. So this current and the current through this 8 ohms from left to right must be the same because they are the same circuit elements. So we can argue that the current through this 8 ohms flowing from left to right is also I0, which is equal to 2 ampere. So after all these steps, we have found out that the current through 8 ampere is, current through 8 ohms is 2 ampere, which is flowing into the parallel combination of 3 ohms and 6 ohms. We can apply CDR for parallel connection of resistances. Here, we know the value of the two resistances. We know the total current, so we can easily calculate I1. Let's write CDR. I1, the total current is I0, which is 2 ampere. Then 6 ohms is our R1, 3 ohms is our R2. So R2 by R1 plus R2 is 3 by 6 plus 3. If we do the calculation, I1 turns out to be 0.67 ampere. Now, often a given electrical circuit can be solved in more than one ways. There are usually multiple ways to solve a circuit. I have solved this circuit using CDR. This circuit can also be solved using VDR. I will not discuss how to solve the circuit using VDR, but I will ask you to solve the same problem using VDR at home. And you know the solutions, so you can compare the results with these calculations and verify whether your solution is correct or not. That's all for today. I'll stop here. Thank you.